Good morning. My name is Akshay, and I'm going to be presenting our paper, Striking a Balance, Pruning False Positives from Static Call Graphs. And my co-authors are Shuyang, Christian, and Jens. So before we start, let's get a little bit of background about static analysis and call graphs. So static analysis tools analyze the program without actually running it and try to find errors and security vulnerabilities in it. And a call graph is a graph of all the method calls in a program and is computed using a call graph construction tool, which itself is a kind of static analysis. So the figure here gives a simplified static analysis pipeline. We start off with a program which is given to a call graph construction tool that generates its call graph. And then we have a null pointer analysis, which can build on this call graph to then produce null pointer warnings. So in this case, the null pointer analysis is said to be the client analysis, the client of the call graph. And to measure the quality of either a call graph or the null pointer warnings, we use two metrics called precision and recall. So the precision definition is out of the static analysis warnings or edges, how many of them were true positives. And it can also be thought of as 1 minus the false positive rate. The recall is defined as out of the ground true positives, how many did the static analysis catch? So we can clearly see that based on this pipeline, that the quality of the call graph will directly affect the quality of the null pointer warnings produced. For example, a null pointer analysis could predict a false positive warning because of a false positive edge in the call graph. So now let's come to the issues with current call graph construction tools. So there are certain user expectations on static analysis tools, and Christakis and Bird conduct a user study to understand these expectations. So they conclude that static analysis tools should aim for 80 to 85% precision. And there are other studies which also support this conclusion. But what about current call graph construction tools? So Vala, one of the popular Java static analysis tools, has a precision of 24% and recall of 95% for its call graph. And other popular tools for Java like Dupe and Peterblocks also have similar characteristics. So note that in this case, to compute these measures, we use the dynamic analysis as an approximation for the ground truth. So why does Vala have these precision and recall characteristics? And the reason is that it was originally designed as a verification tool. So the idea was to have 100 or a near 100% recall, and then to have, and given this constraint, to have as high precision as possible. But there seems to be a gap between the precision that Vala provides and the precision that users seem to expect. So what can we do about this? So this figure here gives an overview of our solution. And it starts off the usual way, where we feed a program to a call graph construction tool, which generates a call graph that has 24% precision and 95% recall. And this is where we add in a new unit called the call graph pruner. So the call graph pruner post-processes this call graph to generate a pruned call graph that's going to have 66% precision and 66% recall. So now we've balanced these two competing metrics of precision and recall, and we're much closer to meeting the user expectations on precision. So let's take a closer look at how we get this call graph pruner. So our solution can roughly be divided into two components. The first component is a classifier generator. So this is an ahead of time learning process that's going to generate a classifier. And as the name suggests, the classifier should ideally be able to classify an edge as a true or a false positive. And we're going to use this generated classifier in the call graph pruner. So the classifier generator can be thought of as a function that takes in three inputs: a static call graph constructor, a dynamic call graph constructor, and a set of programs. And it generates as output a classifier. The call graph pruner, which is the second component, can be thought of as a function that takes as input an existing call graph, the classifier learned by the generator, and a threshold, and outputs a pruned call graph. So the threshold used in the call graph pruner is a hyperparameter that sets how aggressive the call graph pruner is going to be in its pruning. And we'll talk more about it soon. So let's look at one of the components, that is the call graph pruner. So here is an example program, and it has a main function which calls getObjectC and then makes a call to foo. And there are three classes, A, B, and C, with B extending A and C extending B. And each of them implement a foo function in which they make a call to toString. Further, class A has a field F, which is uninitialized and hence could potentially be null. So let's get to this, this call to getObjectC. Now let's assume that it always returns an object of type C, but the static analysis due to over approximation concludes that the function could either return an object of type A, B, or C. And so the variable X could point to A, B, or C, and the function called x.foo now has three possible targets. But we know that only the call to c.foo is really a true positive. Now, if we run a null pointer analysis on top of this call graph, we will conclude that since the field F is uninitialized, the parameter x.f could be null, and then the parameter in each of the three foo calls could be null, and as a consequence, each of the three toString operations could result in a null pointer exception. However, we know that only the c.toString call is really a null pointer exception, and the other two are really false positives, which stem from the false positives in the call graph. So what can we do about this? Recall that our solution using a call graph pruner uses a component called the classifier. So in this case, we're going to use a simplified classifier, which is a decision tree, but our actual implementation has a more complex classifier, which is the random forest, and that is an ensemble of decision trees. So what this classifier is going to do is it's going to examine an edge and give out a probability that the edge is a true positive. And this decision tree classifier here uses two features in its node. So a feature is some information about the edge that will hopefully help us decide whether or not it's a true positive. So the two features here are the destination in degree of the node and the source node out degree of the edge. So going back to the previous slide, let's examine the edge from main to b.foo. It has a source node out degree of 3 and a destination node in degree of 2, with one edge from a method that is not shown. Okay, so now that we have the source node out degree and the destination node in degree, we can start the root node and follow a path based on the conditions in each node. And in this case, we would trace the path false, true, true, and end up with 40% probability for the edge from main to b.foo being a true positive. So let's label this number on our call graph. So the edge to b.foo has probability 40%, and using a similar approach, we can also get the probabilities on c.foo and a.foo. At this point, we can set a probability threshold. So let's say we set a threshold of 50%. We would prune all edges that have less than 50% probability. And so we prune out the two edges to b.foo and a.foo. And as a consequence, when we run a null pointer analysis, we'll prune out the two warnings at b.toString and a.toString, while retaining the one true edge and the one true null pointer warning. Now let's look at the second component, which is the classifier generator. And the high level idea is we're going to cast our problem of predicting if an edge is a true or false positive as a machine learning classification problem. And then we can use an off-the-shelf classification algorithm to solve it. So the classifier generator starts off with a set of training programs and computes a static and dynamic call graph for each of them. Then for the program, we generate a table where each row is one static call graph edge, and the last column is the ground truth label. So since we're using the dynamic call graph as an approximation from the ground truth, if an edge in the static call graph is also in the dynamic call graph, we give it a label of 1. Otherwise, we give it a label of 0. So the remaining columns in this table are features, much like the source node out degree and the destination node in degree that we saw in the example. So once we have a table like this for each program, we can concatenate it into a single training set and feed it to an existing classification algorithm, which in our case is random forest. And the output of this is going to be a trained classifier. So we saw the features that we used on the previous slide. Now let's look at how we pick them. We want 3 properties from the features, in addition to having some correlation to its probability of being a true positive. So firstly, we want a linear time complexity so that it has low overhead. Secondly, we want it to be interpretable in order that we may understand why the edges are being pruned, and we want it to be generalizable so that it can be applied to programs. It can be applied to unseen programs that are not from the training set. And thirdly, we wanted to treat the call graph constructor as a black box so that it makes no assumptions about what kind of tool is being used or what call graph algorithm is being used. So we won't go into details of each feature, but the high level idea is to capture the structural context of the edge in the call graph. So now coming to the data set, we use the NJR dataset, which is a collection of Java programs from GitHub. And it has roughly 293 programs that are amenable to both static and dynamic analysis. So from this, we filter out 141 programs that we know have high dynamic analysis coverage. And this is important because we are using the dynamic analysis as an approximation for the ground truth. So it's important for the dynamic analysis to have high coverage. So these programs have on average 68% coverage. Then we split these 141 programs into 2 mutually exclusive sets. One is the training data set that has 100 programs and which constitute roughly 860,000 edges. So that gives our classifier nearly 1 million edges to train on, and that's more than sufficient. And the remaining 41 programs form the evaluation data set. So coming to the main result of the paper, this graph gives the recall and precision of the original call graph as well as our pruned call graphs. So let's start off with the black triangle, which is the baseline VALA 0 CFA, and it has 95% recall and 24% precision. And the green and blue triangles, which are dupe and Peter blocks, are also in this high recall, low precision portion of the graph. The black curve now is what we get when we apply the call graph pruner to VALA. So we're getting a curve here instead of a single point because because the call graph pruner uses a probability for every edge. So by setting different thresholds, it can get different points on the precision recall curve. And the black curve is what we get when we connect all these points. And the green and blue lines similarly represent the call graph pruner being applied to dupe and Peter blocks. One interesting point is the square, so we have the black, green, and blue square really close to one another. And that is at roughly 66% precision and recall. And that is the point where we balance the two requirements of precision and recall. And we also meet the user expectation on precision. A third interesting point is the red cross, which is the VALA 1 CFA point. And it has a small precision improvement over the 0 CFA, but it's not as high as that that we get by at the balanced precision recall point for the call graph pruner. However, note that a client analysis may still prefer the VALA 1 CFA if it wants precision boost without losing any recall. And as far as the analysis time overhead is concerned, the call graph pruner only adds 18% to the 0 CFA analysis, whereas the VALA 1 CFA increases the analysis time by 292%. So now let's look at how this improved precision affects the output of a null point analysis. And we're going to use the null point analysis by Hubert et al. So with the original call graph, we had 223 errors, out of which only 60, or that is 27%, were true positives. So you can imagine a developer who sees almost 3 out of 4 errors being false positives and is going to be very unhappy with the tool and possibly even ignore its output entirely. Whereas with the prune call graph, we get just 20 errors per program, out of which 15 are true positives. But we have a really high precision. That means that most of the errors that the programmer is going to see are all true positives. So as far as the related work goes, there are 3 main directions. The first involves running a dynamic analysis and collecting some dynamic information and using that to improve a static analysis tool. The second tries to apply machine learning to eliminate false positive error reports from static analysis. And the third direction tries to improve call graph precision using some heuristics or some user involvement. And I won't go into further detail because the details are in the paper. To sum up our approach, we generate a call graph pruner by applying machine learning on a large number of static and dynamic call graphs. And as a result, we generate this call graph pruner, which, along with an existing call graph construction tool, can produce high precision call graphs. And a null point analysis that uses this prune call graph has a significant precision improvement. So that concludes our presentation, and I thank you all for listening.